Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to be doing gas stoichiometry, and then we'll talk a little bit about real gases at the end. Let's get started. Let's do some stoichiometry with gases. Before we start our first problem, I want to talk about standard temperature and pressure. Standard temperature and pressure is defined as 1 atmosphere and 0 degrees Celsius. Usually we use the acronym STP for standard temperature and pressure. Now, when we are at STP, the volume of 1 mole of gas is 22.4 liters. This is called the molar volume of the gas. It is a great constant to use for stoichiometry at STP. Now for our problem. Most outside grills use propane as a fuel. When propane burns, it produces carbon dioxide and water vapor. The chemical equation is shown below. So here is our chemical equation. The wonderful thing is they have already balanced it for us. How many grams of propane are needed to produce 52.6 liters of carbon dioxide at STP? Knowing that it's at STP is critical for this problem because that tells me we can use our molar volume. So starting with our 52.6 liters of carbon dioxide, we are going to use our molar volume to convert that into moles. So here is our molar volume. You can see how my liters cancel. I am left with moles. So I have 2.35 moles of carbon dioxide. Now that I am in moles, I can do my stoichiometry. So rewriting my 2.35 moles of carbon dioxide, I use my mole ratio right here to convert to moles of propane. Notice my moles of carbon dioxide cancel. Our problem asked us for grams, so I will simply convert my moles of propane into grams of propane. Here is the molar mass. Making sure my moles cancel, I am left with grams of propane. So my final answer is 34.5 grams of propane. You can see that molar volume makes converting liters to moles super easy. It's wonderful, but please be careful with it. It only works at STP. So let's do a gas stoichiometry problem that is not at STP. The decomposition of potassium nitrate is shown below. And they've given us our equation, and it is balanced, which is wonderful. What will the pressure in atmospheres of the oxygen be if 14.52 grams of potassium nitrate decompose? So the reaction occurs at 51.5 degrees Celsius and is contained in a vessel that is 1.5 liters. I am going to start with my 14.52 grams of potassium nitrate and work my stoichiometry piece first. So rewriting my 14.52 grams of potassium nitrate. Of course, to do stoichiometry, I have to be in moles. So here's my molar mass. My grams cancel. Now that I'm in moles, I can use my mole ratio to go from potassium nitrate to oxygen. So here's my mole ratio. My moles of potassium nitrate cancel, and I get 0.0718 moles of oxygen. My problem did not ask me for moles of oxygen. It wants to know the pressure. However, now I know the moles, the temperature, and the volume. This tells me use ideal gas law. Here's my equation for ideal gas law. Before I plug my numbers in, I need to decide what value of R I'm going to use. Here are my values for R. My problem asked me to give pressure in atmospheres, so I am going to use this value of R because it will give me my pressure in atmosphere. I could have possibly used this value for R, but volume is measured in meters cubed, and I have liters. Now let's plug in everything we know. We do not know the pressure. That is what we're trying to find. Our problem gave us our volume, our 1.5 liters. Of course, we use our stoichiometry to calculate our moles. We determined our value of R based on our units. And here you can see I converted my 51.5 Celsius into Kelvin. Before we solve for pressure, let's make sure our units match. So volume is in liters. We have moles. And temperature is in Kelvin. And this will give us our pressure and atmosphere, which is exactly what we wanted. So now, solving for pressure, I get 1.27 atmospheres. So far, we have assumed that all the gases we've worked with have been ideal gases, but not every gas behaves ideally. So let's talk about conditions where real gases behave most like ideal gases. Before we look at any plots, we are going to define ideal behavior. So here I have written my ideal gas law. I am going to divide both sides by this term here. This is my next step. Of course, the right side of the equation simply goes to 1. So now I have PV over nRT equals 1. This is the behavior of an ideal gas. So let's look at a plot with different temperatures. So here is our plot. Our y-axis is our PV over nRT. That is our ideal behavior. And on this plot, our ideal gas should give us a horizontal line right here. Of course, these are real gases, so they do not give a perfectly horizontal line. But which ones get close? So you can see I have several temperatures plotted. My purple line is 173 Kelvin, and you can see I deviate strongly from ideal behavior. The green line is 298. I'm getting a little bit better with the green line, but you can see my 873 really starts to look horizontal. So as temperature increases, real gases start to behave more and more like ideal gases. But what happens with pressure? Still keeping our ideal behavior PV over nRT equals 1. Here is a plot showing high pressure. Again, my y-axis gives us PV over nRT, and my ideal gas should give a horizontal line there at 1. Here are several gases. My carbon dioxide probably gives the worst in terms of ideal behavior, but oxygen looks like it's giving the best. But this is at fairly high pressure here. Let's see what happens when we take this plot, but we drop the pressure. So here is a similar plot, but with very low pressures. And notice how many more of my gases are behaving much more like my ideal gas, which should give a horizontal line at 1. So real gases at low pressure will behave more like ideal gases. So while no gas behaves perfectly like an ideal gas, if we combine high temperature and low pressure, we are going to get the closest to ideal behavior. Remember, you must be at STP to use the 22.4 liters per mole. It's very tempting, I know, to apply it to other situations. So be careful out there. Thanks so much for watching.